All right, it's time for another question show. Your questions, my answers. As always, wherever you are on my channel, if a question pops into your brain, just type it in. I'll gather them all up and I'll answer them here. I got another special guest answerer, Emily Lakdawalla from the Planetary Society. She's going to talk about curiosity. What else? So stick around for that. All right, let's get into the questions. SnowToad, my two favorite space channels. This was just in reference to the live QA that I did with Isaac Arthur, and that was super fun. I also did a live QA with Cody from Cody's Lab. I'm going to be talking to John Michael Gaudier. Paul Matt Sutter is going to be coming up, and I'm going to try and queue up special guests as many weeks as I can. These happen on Mondays at 5 p.m. It's a totally live event, so you can join us live, ask your questions, just join in the chat, and we'd love to have you there. So it's just like another thing that we're going to be doing. And a big thanks to all the patrons who have been contributing, supporting, giving us sort of more opportunity and ways to be able to reach out and connect with the audience and bring more people in. So thank you. So I know that wasn't a question, more of a shameless self-promotion about the live event that's coming up, but please come and join us. All right, Clim hazzard. Are lava tubes generally considered to be stable enough for something like a colony? Would they need to be reinforced? I did that whole episode on lava tubes, and I got this question quite a bit. And, you know, these lava tubes that are on the moon and Mars, the only reason we know they're there is because the tops have collapsed in and there's rubble sitting on the bottom of the lava tube. And in some cases, like say on the moon, these lava tubes can be 10 kilometers high. So you can imagine like the roof caving in and chunks of rock falling 10 kilometers onto your colony down below. So that is definitely a risk. At the same time, both Mars and the moon are essentially geologically dead. So they probably don't have any significant Mars quakes, moon quakes of any, of any large magnitude. In fact, there's a spacecraft, the Mars Insight is going to be going to Mars, and one of its jobs is to figure out just how dead is the interior of Mars. So we'll know better sort of what are the likelihood you're going to get some kind of earthquake. There could, of course, be some kind of meteorite impact on the surface that could cave in more of the surface. But these things have been there for billions and billions of years, so the chances of it caving in within the few decades of when we set something up. But I'm sure people will feel a little nervous to look up and see this ceiling of rock and think of ways they're going to try and reinforce them. So I can imagine over time they will reinforce them. But in the beginning, it's probably safe, probably. Yes, in 2828. Hey Fraser, how likely is it for a rogue planet not bound to a star to intersect our solar system without us detecting it? Well, by the time I'm recording this, we just survived the April 23rd Nibiru flyby, April 24th Nibiru flyby. Now, I've been debunking this idea of a rogue planet for, I think, my entire space journalism career. So I think we've been debunking it for close to 20 years now. And I know there's a lot of channels that are like, they just update, they leave the video the same and then they update the date a couple of days later. Like, oh, now the world's going to end on May 5th. Now the world's going to, there's no Nibiru, there's no planet. There is no rogue planet that we are aware of that's anywhere near the solar system right now. And if we could, if it was there, we would be able to detect it and know decades out, if it was going to cause us any problem. Is it possible for a rogue planet to come through the solar system? Absolutely, right? We know, based on the discovery of the Oumuamua asteroid, that objects from other solar systems come through the solar system all the time. In fact, it's estimated that there could be 30,000 interstellar asteroids in the solar system right now. But the solar system is a very big place, right? That sort of the amount of gravity, the Oort cloud is thought to extend out to a distance of maybe 2 light years. So it's a very big place. What you're really wondering is, what are the chances of a rogue planet coming right through the center of the solar system and maybe affecting the gravity of various planets as it goes through? And the reality is very, very low. We don't know what's happened in the past, but here we stand 4.5 billion years after the sun formed and the planets formed. in that 4.5 billion years, it doesn't seem like any large objects have moved through the solar system and severely disrupted our orbits. It's a thing that we would detect. So the chances of it happening anytime in the future are still pretty low. So those rogue planets are out there, but it doesn't sound like they interact with our solar system very regularly. But I'm sure if we run the clock forward billions, trillions of years, there could be some interaction. But, you know, I would put that very low on the things that you're going to have to worry about. Cliff Marsden. Couldn't we use a massive lifting balloon filled with hydrogen to get spacecraft high into the atmosphere and then use the hydrogen as fuel for the next stage to leave Earth? I've gotten this question quite a bit from people, and you're essentially talking about this idea of using a balloon to launch a rocket. And when you think about rockets, right, there's two parts to what a rocket needs to do. The first thing is that it needs to get up through the atmosphere, but the sort of the bigger velocity change is that it needs to be going 28,000 kilometers per hour sideways. So really the rocket has got to push through the atmospheric density, it's got to build up that speed, and it's got to go sideways 28,000 kilometers per hour. So if you did get a balloon up and you launched a rocket from that balloon, you would save having to go through the atmosphere. So you definitely save yourself some fuel, but not a lot of fuel, because the big part is going the sideways part. That said, there are a couple of companies that are working on this thing. There's one called Leo Aerospace, and they're developing this exact idea. And then what they're seeing it is it's more for the small launch market. So imagine, say, people who have a CubeSat, but they don't really want to piggyback on any other big spacecraft because they have some specific orbit that they want their CubeSat to go on. This is a good solution. You have a big balloon, lifts up the rocket, and then the rocket takes off from the balloon and goes sideways into this final orbit. Now the big problem is, what do you call these things? Now they're calling them raccoons, and I don't like that at all. I've heard blockets. That's no good. So I think this whole technology is waiting for somebody to come up with a good name. And then once a good name comes up, then we can actually move forward with this technology. I think it's also important to remember that there's a tremendous amount of very low cost, small launch providers that are now popping up all over the place. There's the Electron rocket from Rocket Labs. There's a lot of other small launch providers popping up all over the place, and every idea is being tested out. There's aircraft-based rocket launches. There's these balloon rocket launches. So I think we're going to see a lot of just great variety over time, and whatever works out best is going to sort of get adopted. And there's great to see this market now on the small end of the launch providers. Someone's working on a electromagnetic launch system, like a railgun. So there's a ton of variety going on, and I can't wait to see sort of what happens over the next couple of decades as these get tested out. Disaster arena. What's the easiest place in the solar system from which to extract resources? The Venusian clouds, the lunar regolith, the Martian polar caps, you get the idea. Those are all actually pretty tough. The easiest place to extract resources in the solar system is going to be, well, Earth, obviously, if you're on it. You don't have to get out of the gravity well. But if you have to get out of the gravity well of Earth, you're going to want to find asteroids which have a very close orbit to the Earth. There's examples like asteroid Toutatis, and there's a few others like that have a very similar orbit to the Earth. They're just a little further out from the sun, or maybe a little closer into the sun. And you can imagine sort of in the future, you know, some spacecraft getting into low Earth orbit, and then it only needs a little more change in velocity to reach one of these asteroids. It's almost, you know, it's like only a little harder to get to than to get into Earth orbit. To get to the moon requires a lot more velocity. To get to Mars requires a lot more velocity. To try and get material out of the Venusian atmosphere is going to be really tough, because you have to drop into Venus's gravity well, which is about the same as Earth. So really the bottom line is, you don't want to go into gravity wells. Gravity wells are for suckers, and you don't want to use a lot of change in velocity to reach your target. Now, the big challenge, of course, is how hard is it going to be to extract resources off of these asteroids? and we just haven't developed the techniques. Their gravity is very low, so it should be easy to get the material off of them, but it's also very low gravity, so you don't have a lot to work with. So there's going to be a lot of engineering and technical challenges, but that's going to be the easiest places to get resources out in space. A night that says knee. I've heard that our planet is gaining weight every year due to asteroids. Is this true, and what is the consequences, besides never getting a date, married, and thus no rings? So that's why the Earth doesn't have rings. That makes sense. Yeah, so there is material falling into the Earth all the time. And of course, you see it when you go outside and you see falling stars. It's this interstellar, interplanetary dust that is just falling to the Earth all the time. And there's small ones, but of course there are much bigger ones, right? Things like Chelyabinsk, which actually happen, a couple of times a year, mostly above the oceans. But there are big objects falling into the atmosphere all the time. So apparently there are tons and tons of material that fall into the Earth. At the same time, though, the sun is actually blasting away our atmosphere. And so the atmospheric loss and the amount of infalling material kind of balance out. They're within sort of an order of magnitude of each other. So it's hard to say whether the Earth is getting fatter or it's getting thinner, depending on whether you're talking about rock, right? It's getting more rock and it's getting less air every year. Jim Becker. Fraser, I was watching part of your telecast, Astronomy Cast 488 Dark Energy 2018 edition, and I have to ask, why does it seem like it is up to the U.S. to pay for all 90% of these telescopes and research tools looking for things that the world scientists seem to want? It seemed like I kept hearing, well, Trump blocked this or Trump doesn't want that. And why can't the rest of the world pay for their share of the research tools? Astronomy Cast. I'm going to give a quick shout out to the Astronomy Cast. We just did episode 488. We're doing updates on all the different kinds of discoveries, dark energy, dark matter, black holes, supernova. What are they? What have we learned in 10 years? So if you want more space science goodness, go check out Astronomy Cast. So in the context of that episode, we were talking about some dark energy missions. And so every 10 years, right, the US government asks the scientists to gather together to do their decadal survey, their 10-year survey, and say, what are the big science objectives that you have and want, and you want us to then fund to develop? And a lot of the spacecraft that you're familiar with are the outcome of these decadal surveys. So the scientists all get together, they decide what their big science objectives are, they pass that back to NASA. NASA then builds the space satellites or ground missions or anything to try and answer these specific questions that the scientists had. And the problem that we're having now is that there's a break in this. So in other words, they were asked what their priorities were, and then a lot of these missions are potentially getting canceled. So that's a little frustrating. To say that the United States is expected to pay for all these missions is kind of crazy, right? So there's the European Space Agency. They produced the Planck mission, which has produced the best view of the cosmic microwave background radiation. I just did a big video on the Gaia mission, which is just fountaining data. There's the ExoMars mission. There's the Bepi-Colombo mission, which is off to Mercury. ESA is generating a tremendous amount of missions and scientific data. They're going to be working on the LISA mission, which is going to be the best way of examining gravitational waves. They're working on the biggest fusion experiment in the world at ITER. They've got CERN based out of Switzerland and France. And although the Americans are very involved in that and have helped out with some of the experiments, it's a European mission. But that's just the Europeans, right? The Indians have launched their Mars mission, and they're coming up with a new mission that's going to be going to the moon. The Japanese have their missions to the Hayabusa missions, and they've got other missions in the works, and they've done a mission to the moon recently. The Russians have launched missions in recent memory. There's the Chinese are coming on strong, and they've got the biggest satellite telescope, the biggest sort of permanent satellite telescope, radio telescope in the world. They're going to be building the biggest steerable radio telescope in the world. Canadians, of course, we've got this amazing CHIME instrument, which is going to be used to determine what fast radio bursts are. There's the Square Kilometre Array, which is in South Africa and Australia coming together. There's all of these enormous observatories in Chile, which are funded by the European Southern Observatory. I could go on and on and on and on and on. I could do this all day. So it's just that I think the frustration in the scientific community is that the American scientists are frustrated that the missions and science objectives that they wanted to achieve have been stymied by the various administrations. And it's not just it's not the White House administration, it's just sort of the overall political system entirely that changes objectives, that puts political needs in front of sort of the science needs. And I think for a lot of scientists, they feel like it's a very frustrating time to be trying to do science work in the United States today. And if anything, I think the United States is going to be falling further and further behind as these other countries are stepping up and developing these missions and pushing this knowledge forward. So I think it's the opposite, and I think it's going to become more and more apparent over time. And so there you go. Headless Horseman MC. Hey Fraser, why do you only talk about SpaceX and not Blue Origin? I talk about Blue Origin whenever they have interesting news to announce. They just launched the 8th launch of the New Shepard rocket, which is this suborbital rocket that they're going to be doing space tourism in, so you can go up and experience a little bit of weightlessness. But the reality is that right now, Blue Origin keeps what they're up to pretty close to their chest. They've got this amazing rocket motor called the BE-4 that other people are going to be picking up, and it's probably going to replace all of these imported Russian rockets that are being used. And then, of course, they're working on their new Glenn, which is going to compete against what's happening with SpaceX. But the reality is that they just are not, they have not done the test. They have not launched these rockets. They have not demonstrated their ability to keep up with SpaceX. As soon as they do, I'll be all over it. As soon as they release more information, I'll be all over that. But of all of the sort of big rocket companies right now, Blue Origin is pretty secretive. I just learned that Jeff Bezos spends $1 billion personally of his money on like he sells $1 billion of Amazon stock every year and uses that to fund Blue Origin, just out of pocket. So I don't recommend anyone bets against Jeff Bezos. He is like the richest man in the world. He's a formidable opponent. He's got deep pockets, and he's got this strength of character and will that I think we're going to see Blue Origin succeed. So stay tuned. As more interesting things comes out of Blue Origin, I will announce it. I will talk about it. I can't wait. Oh, and one other thing. I actually personally like Jeff Bezos's rationale for why to build a spacefaring civilization over Elon Musk's. Elon says, I want to send people to Mars to use that as a backup for humanity. And Jeff Bezos says, I want to get all of the heavy polluting industry off Earth to make Earth better. And I really like that rationale. So, Peter Van Gimmert. Deep Space Gateway is a ripoff for the US taxpayer. This thing serves no purpose. Go to Mars. Stop wasting time and money. Want to know a thing that's going to cost a lot of time and money? Going to Mars. And in order to go to Mars, you're going to need to learn to survive in space under the harsh conditions, away from the Earth's protective magnetosphere for months, potentially even years. And the only way to do that, to learn about that, is to build a space station that is outside of the magnetosphere where people can be there for months and maybe years and figure out what is the true radiation load that's going on out there, what are some of the other dangers, what is the danger from micrometeorites, how do you eat, how do you deal with a closed system of oxygen and water and all of this. So there are a mountain of challenges, of unknown engineering problems that have not been solved yet, and the only way to do that is to just put human beings in space, far away from the Earth, and try to make them not die. And once you've sorted that out, then take all those lessons and go to Mars. And if that isn't figured out, then you can expect the Mars mission to be even more expensive, even more costly, even more time intensive, and you're going to be like 10 times as disappointed with the trips to Mars. Moser, 1977. question that popped into my brain: what powers the enormous storms on Jupiter? The entire planet is a giant storm. Where's the power to run that coming from? So think about the Earth. Inside the Earth, we've got the crust, and then we've got the mantle, which is like molten rock. And then inside that, we've got the core of the Earth, which is rock that's at like 25,000 Kelvin. That's really, really hot. And that is the leftover heat from the formation of the Earth 4.5 billion years, as well as decaying radioactive elements. So Jupiter is the same thing, and Jupiter is bigger. So in the core of Jupiter, I think the temperature is like 1,000,000 degrees Kelvin. And so that heat radiates outward and is the power for Jupiter. Now, the actual outside temperature of it is exposed to space, and so it's cold, and you get this difference in temperature from the core of Jupiter, which is the leftover heat from its formation and sort of its compacting down on itself. Can't quite turn into a star, but it still generates a lot of heat from that internal pressure, matched with the outside of it, which is freezing cold and exposed to space, plus all the sunlight that's coming in on it, and that all runs the Jupiter storm system. Rhetorical question: does Curiosity send back raw data, or it processes and identifies the minerals before sending it back? That is a great question, and that sounds like a question for a person who has studied Curiosity rover more than anyone I can even think of, and that's my friend Emily Lakdawalla at the Planetary Society. Now, Emily has written a new book, The Design and Engineering of Curiosity, How the Mars Rover Performs Its Job, and this is a comprehensive book about what's going on inside the Curiosity rover. How does it work? Every instrument. I think someone from NASA said that if Curiosity had a glove box, this would be the book that's inside it. And Emily answers that question.
Curiosity sends back raw data from its instruments. It's actually a difficult process to identify minerals from the data that we get from Curiosity's instruments, which are really sophisticated. In the case of one of its experiments, the SAM experiment, they actually have to run experiments on Earth with what they think they got in the Mars in the Mars rover's experiment in order to be really sure that they got what they think they did. So there's actually quite a lot of interpretation that has to be done on Earth in order to understand the data that we get sent back from Mars. And one of the good things about that is that it means that scientists are going to be busy for many years, even after the Curiosity mission is over, getting more and more little details out of the data that the rover sent back to Earth.
All right, thanks, Emily. Now I'm going to put a link to Emily's book. I'm going to put a link to Emily's blog over at the Planetary Society. Remember Bill Nye, Planetary Society, Emily Lakdawalla? You should totally check it out. That's it. Thanks, everyone, for asking all your questions this week. I really appreciate it. It's a lot of fun. As always, wherever you are on my channel, if a question pops into your brain, just go ahead, type it out, and I will gather them up, and I'll answer them here. I'll see you next week.